All right, we're going to pick up about power series and talk a little bit more about them. We introduced those in a previous video, but then we spent the rest of the time talking about just polynomials, Taylor polynomials, and things like that. So we're going to go back to this idea of the infinite series, the power series. And we're going to talk a little bit more about them specifically before we link these up with specifically the Taylor series. That's kind of what we're moving towards here. We're going to take those Taylor polynomials and stretch them out to an infinite degree using some power series stuff. But to do that, we should know a little bit about power series. So here we go. First, we're going to recap the geometric series. This is not a power series because there's no variables in here. We have a fixed ratio r raised to some exponent, and the reason we're going to talk about that is because it's one of our nicest series in that we know everything about it. We know when the geometric series converges. We know specifically what it converges to. There are not many series that we have that information about. Then we'll move on to talking about how a power series can converge, do some convergence testing on them. We'll talk about properties of power series, and then we will do some examples where we find some power series representations of functions using all the stuff that we're going to talk about. So here we go. Let's start off with a quick recap of the geometric series. So this is our general form of a geometric series, this a r to the k, where you can have a coefficient if you'd like, but then you have this fixed ratio raised to the exponent k. And we know that when it converges, specifically when the absolute value of this ratio r is small, less than 1, it converges to specifically a over 1 minus r. We're going to look at a simple form of it where this coefficient a is just 1, so we're really just going to look at the singular r to the k. And then it converges to 1 over 1 minus r when the absolute value of r is less than 1. Diverges otherwise. Cool. What we're going to do is just extend this to a power series with, instead of r, a ratio, being raised to this exponent k, we're going to leave that as a variable input that you could think of as a ratio being raised to an exponent k. And we have that it's going to converge specifically to 1 over 1 minus whatever that ratio was, but now that ratio is x instead of r, and we have the same conditions for convergence. Now, if you want to think about this, you can think that this is like a function then. We have this f of x equals 1 over 1 minus x, and this is almost like a built-in domain. It's an interval of x values for which this series converges to this function value. So that's kind of interesting. We're connecting this power series with something almost akin to a function. So let's talk about power series more, and we'll see this connection hopefully continue to build up as we talk about them. We're going to talk about how a power series converges. So what we noticed is that we had this interval of x values earlier, so that's going to be interesting. So here's our general power series. We've got a center, a, we've got this sequence of coefficients, right? Those are all just real numbers. And then we can say that when this converges, it's actually going to converge for a set of x values. So we'll call that set an interval of convergence. In that geometric series that we had, that we went over to just build the basic power series x to the k, our interval of convergence was negative 1 to 1, because those were the criteria for that geometric series to converge. We can also think about the distance from the center to the endpoint. So if you think about maybe a number line here, and you've got your center here at a, and you've got your interval of convergence going out this way, then you can say that this distance here is this capital R radius of convergence. So you could almost think that your interval of convergence is like a minus r up to a plus r, right? It's the center plus or minus some distance, and that distance we'll call the radius. Hopefully it's pretty obvious why we're calling this a radius. The radius of a circle is the distance from the center to the outside edge of a circle. And so the radius of this interval is the distance from the center, A, to the outside edge of that interval of convergence. So this is just some features that we'll be looking for. When we talk about convergence of power series, we're not just going to classify them as converging or diverging or even maybe like absolute convergence or conditional convergence. What we're going to talk about is convergence on an interval of x values, and we're going to try and find that interval of x values. Quick note, we're going to use our regular series testing to do this. But because we're looking at these specific power series, a lot of our tests are going to fall out to just be ratio or root tests. Every now and then, excuse me, we'll relate things back to geometric series, but you're going to see a lot of ratio and root tests. So if you need to go back and review what those are, look at the conditions for what it means for when things converge or diverge on those, or when the ratio and root tests are helpful, all that kind of stuff, absolutely go ahead, pause this video, open up your notes, switch into a new tab, whatever, find some help on that stuff just to brush up on it. All right, here's some examples of convergence testing. For something like this, I'm going to use the ratio test, and notice what I'm going to report here. This IOC is going to be my interval of convergence, and then we'll report the radius of convergence as well. We can take a look and see what we think the center might be just based on the structure here, but we can also see that in the interval of convergence and that kind of thing. So anyways, you might notice that we've got this nice factorial in the denominator that is like a screaming siren yelling, do the ratio test, do the ratio test. So let's go ahead and do the ratio test. What we'll remember is that the ratio test only works for positive terms, so we're going to need to apply some absolute values to this up here. Notice that if x is a variable, it can take on, right now we're saying any value. We're not going to put any limitations on it. And so for doing the ratio test, we're going to kind of treat this like it was almost a non-positive term series where we have to look at the absolute values of things. So we're going to look at the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. And instead of writing this as this big stacked fraction, I'll look at this and say this is the absolute value of x to the k plus 1 over k plus 1 factorial times k factorial over the absolute value of x raised to the k. I can pull this exponent out if I want. There we go. All right, and then we can do some canceling like we normally would. We'll say these factorials are going to cancel nicely. We're going to be left with a k plus 1 on the bottom. So we have a limit as k goes to infinity with this nice k plus 1 in the denominator. And then we'll also notice that these exponentials are going to cancel out really nicely, where we're going to be left with just a single copy of the absolute value of x up in this numerator. Now, this limit can sometimes feel tricky. Every now and then students will look at this and say, oh, okay, infinity over infinity, so it's L'Hopital's rule, so we got to differentiate the top and the bottom. But no, we got to wait and pause for a second to see what's actually going to infinity. K is the thing going to infinity. So the denominator is changing, but x doesn't change. As k goes to infinity. So we can treat x like a constant here with regard to k. And so what we really have is this k going to infinity on the bottom. This limit is going to be 0. Now we got to look back and say, okay, what does this mean? We know then that this ratio is specifically less than 1, and that means this series converges. But I want to know what x values does it converge for? Right? What's the interval of convergence? Well, let's think about what happened here. We said that this limit was going to go to 0 no matter what. If you pick any x value and plug it into here and then take this limit, so you put it in and you leave it at what it is, and then k goes off to infinity, the denominator is eventually going to get bigger than the numerator by a huge order of magnitude, right? As long as you pick some finite x value and put it in there, any real number, and put it in for x, this limit is going to go to 0. What that means is that this series converges absolutely for all real x values. So we can say our interval of convergence is actually the whole real number line. And our radius of convergence then you could think is like infinity. Notice the center here is a little hard to tell, right? But if you take a look, our center is actually going to be 0, because normally we have this form x minus a raised to the k, and you could say this is really x minus 0 raised to the k. So the ratio test shows that this series converges for all real x values. Here's another one, and notice that with this one, we've got like a really great time to do the root test. Here we threw in this -1 to the k, which is going to remind us that we have to use absolute values, but we're also going to need absolute values on this x minus 2, because that thing could be negative as well. So when we do the root test, we look at the limit as k goes to infinity of the absolute value of the kth term raised to the 1 over k, or we're looking at the kth root of it. So this is the limit as k goes to infinity of the absolute value of this highlighted alternating -1 to the k thing is just going to be 1. So I'm left with an absolute value of x minus 2. Oops. There we go. Raised to the k over 5 to the k, all raised to the 1 over k, the kth root of this. Notice I don't need absolute values in the denominator because it's already going to be positive. Now I can apply that root to the numerator and the denominator, and I'm left with a limit as k goes to infinity of the absolute value of x minus 2 over 5. And again, students will sometimes say, oh, this is going to be infinity, right? Because the numerator is going to get really big. But wait, k's the thing going to infinity, not x. So this is actually constant. We can treat it like it's a constant because this is constant with regard to k. As k goes to infinity, nothing changes on this. Now, for the root test, we need this to be less than 1. So our series converges when the absolute value of x minus 2 over 5 is less than 1. Now you can do a whole bunch of stuff here to find what x values are going to solve this inequality. What I normally will do is just multiply both sides by 5, and I'll say the absolute value of x minus 2 has got to be less than 5. And then from here, you can either come up with an interval, or you can just visualize a number line, or anything like that. You could say that means that x is going to equal like 2 plus or minus 5, or you could see that this is a center at 2 and the radius here is 5. I like to visualize a number line sometimes, because what this is really saying is that the distance between x and 2 is less than 5. So here's my center. I'm going to go out to here, and this distance has to be at most 5. I can take any x values here, and I can take any x values here. So you can see this is like 2 plus or minus 5, right? We go up to 7, and here we go -3. So our interval of convergence, we might say, is -3 to 7. But we have to be careful about this. Wait. Because what happens if this absolute value of x minus 2 over 5 is equal to 1? Well, in that sense, our root test is inconclusive. So the question is, do we include these endpoints or not? And the answer is actually not hard to find. All we're going to do is test the endpoints. So we're going to say our endpoints are x equals, what were they again? -3 and 7. What I mean by that is I'm going to take a look at this series. It's got an input x, and I'm going to say let's specifically look at the series when x is equal to -2. I go -1 to the k times, or sorry, x is equal to -3. I've got -3 minus, oh my goodness, my talking and writing at the same time is so bad, all over 5 to the k. This series now is k equals 0 up to infinity. I've got -1 to the k times -5 to the k over 5 to the k. Hopefully you can see that this is k equals 0 up to infinity of -1 times -5 is +5. And so we have 5 over 5 raised to the k, or 1 to the k. This is a geometric series technically. The ratio is 1. That means it's too big. But this series is really just 1 plus 1 plus 1 plus 1 forever and ever and ever. This is going to diverge. So for our interval of convergence, I'm going to use open interval on -3. Now, let's go ahead and check the other endpoint when x equals 7. I'll give you a second to do that. Go ahead, plug in 7 for x, and see what kind of series you're ending up with, and test to see if that thing converges or not. Pause the video, see what we can do. All right, let's do this. Oh no, all that time, I could have just taken off my ruler, and I didn't. There we go. We can say k equals 0 up to infinity, -1 to the k times 7 minus 2 to the k over 5 to the k. This is the series of -1 to the k. And again, this is another geometric series. This diverges. Another way that you could think about this is that the partial sums are always going to be 1 or 0, and so the partial sums never converge. But either way, we don't get to include 7 in this interval of convergence. Our radius of convergence, we can go back and see what it is. It's still 5, right? It's this value right here. So that part we could have answered anyways. But we had to tell and see if our ending point was going to be included or not. So anytime you get some sort of an interval that has finite values like this, you've got to test the endpoints here and see, are these ending points actually included in this interval of convergence or not? The way that we test these ending points is, again, to just put those values in for x, and now we're back into just a regular infinite series. No power series anymore with function values, with x values and stuff like that. It's just a regular old infinite series. So, 3 types of convergence of a power series. The series could converge for all the x values. That's like what we found in that first example. So the interval of convergence is -infinity to infinity. The second case is that we might actually have some finite radius of convergence. R is a real number. It's got to be positive. And we have that the series converges for some interval where the distance between x and a is less than r, and it diverges for the distance between x and a being bigger than r. Notice we don't have any statements about what's happening when the distance between x and a is equal to r, so that's where we have to test those endpoints. Make sure that you do that. Notice that we never actually have divergence of a power series, because you can always evaluate this power series at a specifically. And if you do that, if you put in x equals a, it should be pretty obvious what happens. This just becomes 0. And so then you end up with 0 times every coefficient on there. You add up zeros. This is like the trivial case. It's the very, very boring power series. It's not really a power series at all. It's just zeros added up forever. And so, yes, technically that power series does converge at only the center. So that's something interesting. We never get to talk about divergence of a power series, really, because at the very least, a power series will always converge at its center. The radius of convergence, then we'd say, is 0, because it's our center plus 0 minus 0. That would give us our interval. All right, so now that we've talked about how power series converge, and we've done a little bit of testing on these things, let's build some properties of power series. Notice I've got convergent power series in here, but we can classify every power series as a convergent power series at some point, right? Maybe it's only converging at the center, but it still converges there. So here are some properties. We can combine these things in interesting ways. So let's say we've got 2 power series. Notice they're both centered at 0. No big deal. As long as they have the same center, everything works out nicely. But the coefficients look like they're different. One of them is this C sub k sequence, and another one is a D sub k sequence. Maybe the coefficients are similar to each other. Who cares? And let's say that we know that those converge to these functions f of x and g of x, respectively. Because again, That's what these power series are converging to, right? They're functions where we can put in an x value and you get a specific y value output. The outputs here are what the series would converge to specifically for those inputs. All right, so anyways, if you've got that they converge on some interval, then if you add or subtract the coefficient structure together, you can just add or subtract the functions. So you can split this thing up essentially and say this is really a sum of c sub k x to the k plus or minus d sub k x to the k, and then split this up as, oops, I want a c here, not an x. There we go. As this sum plus or minus this second sum. That might seem pretty obvious, but wonky things can happen when you deal with infinite series, so we do need to be careful about stating all these properties correctly. We can multiply things. Notice we're not going to multiply two power series together because you'd have this kind of infinitely big distributive property that you'd have to do. You'd have to multiply an infinite number of things by an infinite number of things in a whole bunch of different methods and ways, and that gets really messy. In general, we won't mess with that. But you can multiply a power function, a single term, by a power series. So we can take some sort of x to the m here and multiply it on our power series, and you'll notice it just adds to the exponent. Now, there are some rules here. We got to make sure that whatever m is, we're going to have these nice positive non-zero, non-negative exponents. Oh, and that's supposed to be an x right there. That looks like a c. I got to fix that in my notes that I put up to you guys, the blank slides. But we can just add those exponents together, and specifically it'll just converge to x to the m times f of x. So what you'll notice a lot of times is you might have something like this, and you'll have to kind of undo it a little bit. It's going to converge for all non-zero x values in that interval of convergence. And for x equals 0, we're going to converge specifically to this limit. The main problem that we have is that when x equals 0, it is possible to divide by 0 here. If m is negative, then it's really in a denominator, and we're dividing. And so then we need to investigate a limit. And the last property that we have is composition. This, I think, is the most important or maybe most fun one to use. It's hard for me to separate importance and fun. So if we have some non-zero coefficient b and a positive exponent m, then you can compose bx to the m, this basically a single term of a power series, a single power function, inside a power series. So normally this would normally be where x was, but now we're composing bx to the m inside of that. And it's going to converge to not f of x with bx to the m put in place. And the only thing that we need to make sure is that the thing that we're composing inside that function is actually in our interval of convergence. So normally we would check and see if an x value is in our interval of convergence. Now we're going to have to figure out what x values make this whole piece in our interval of convergence. But that's normal what we would do for composition of functions. We'd be tracking domains that way. And so it's kind of the same idea. All right, note, for now, the only power series that we know everything about is this basic one. And oh, another typo on here. That's what happens when you string these notes together really fast. It's this basic power series from, oh, and that's supposed to be a k. Oh, I was all over the place. From k equals 0 up to infinity of this x to the k. That was that basic geometric looking thing that we started off with. And we know it converges to 1 over 1 minus x on this interval of convergence, negative 1 to 1. So for now, we're going to try and pretty much link everything to this series, because this is the only thing that we know what it converges to. All of these properties, we have to know that our series converges to a function, right? And so this is the only one where we know exactly what it converges to so far. We'll do more with this, but for now, it's just this geometric looking one. So here we go. Let's find the power series and the interval of convergence for this function. What? So what we have to do is compare this to the only series that we know. And we'll build up this list of series that we know. But for now, hopefully we can see that all we've done is multiplied an x to the 6th in the numerator. So this is really x to the 6th times 1 over 1 minus x. And then we can say, okay, that's x to the 6th times a power series. From k equals 0 up to infinity of x to the k. Now, this is still going to converge on this interval of convergence. Now we can do the distributive property and multiply this power function inside of our series, because again, remember this series is just a whole bunch of terms added together. And so we're really multiplying on all of those terms here. Let's multiply the x to the 6th on the term itself. That's going to give us x to the k plus 6, because we just add the exponents. So here's the power series representation for this function. Now, if you wanted, you could go ahead and do some testing on this to see when it converges. You could think of this as just a geometric series. The absolute value of the ratio, x, has to be less than 1. And so our interval of convergence is negative 1 to 1 again. Or you can notice that was just the original interval of convergence, and multiplying by a power function does not change how things converge. Interesting. All right, so for something like this, if we just notice that this function that we're looking at, x to the 6th over 1 minus x, is actually some other function that we know the power series of, just changed a little bit, we got to figure out how did we change it. Here's another one. How did we change 1 over 1 minus x? You can notice that this is 1 over 1 minus something, but it's not 1 over 1 minus x. So hopefully we can see we composed 5 over x into 1 over 1 minus x. So let's go ahead and compose that into the power series. So we will compose 5 over x into the power series representation of 1 over 1 minus x. So this is our series from k equals 0 up to infinity of not x to the k, it's 5 over x to the k. Or if you want, you could say, whoops, that's supposed to be 0. There we go. You could say 5 to the k over x to the k. And this is our power series. All right, what's our new interval of convergence? Well, you can either think of this as a geometric series and see, oh, okay, here he is. Here's our ratio, absolute value of 5 over x. That's got to be less than 1. And now we can go ahead and mess around with this thing, figure out what's going on here. You notice that we're going to need big x values, right? So we could say, all right, our interval of convergence is going to be negative infinity up to 5, union 5 up to infinity. Big x values is going to make this thing real small. And so obviously then really, really negative ones will do it as well. Or you could say 5 over x needs to be in the original interval of convergence from negative 1 to 1 and solve that way. Pretty much the same thing though. Whether you're thinking through this ratio on this geometric series or trying to string together how can we make 5 over x be in our original interval of convergence of the power series that we manipulated. It's all the same thing. Cool. Here's another one. Notice that we've got two differences here. We switch this sign from minus to plus, and we've got an exponent here. So, take a second, see if you can figure out how you manipulate, or how we would manipulate this 1 over 1 minus x function to get 1 over 1 plus x squared. Once you've got that, you can start setting up your power series representation for it, but we'll pick things up there. Pause the video and see what you can do. All right, let's do it. What you'll probably notice is that if we call this thing g of x, then this is really g of negative x squared, right? Because then it's 1 over 1 minus negative x squared. That's going to give us our 1 over 1 plus x squared. So what we've done is we composed negative x squared into 1 over 1 minus x. So let's compose negative x squared into the power series for 1 over 1 minus x. That means this function is equal to this power series with a negative x squared raised to the k. Now I'm going to go ahead and split that apart because the negative 1 coefficient I'm going to pull out and put a k exponent on it, so it's alternating. And then x squared raised to the k is really x to the 2k. So this is the alternating series with even exponents, right? You put in 0, you get an exponent of 0. You put in 1, you get an exponent of 2. If you put in 2, you get an exponent of 4. Multiplying these exponents by 2 is just forcing this to be even for our exponents. Our interval of convergence, we can say either take a look at this right here and say the absolute value of negative x squared needs to be less than 1, or we can say negative x squared needs to be in our original interval of convergence. And either way, what you'll notice is that our interval of convergence, is negative 1 to 1. Cool. We're almost finished with this. We've looked at a bunch of these properties, but there's one other property that we can think about. The real advantage to dealing with a power series, an infinitely long string of power function terms added together, is that differentiation and integration are really, really easy. Because what these are just infinite degree polynomials, essentially. And we know that power rule is about the easiest derivative rule or antiderivative rule that we can apply to things. And so if we want to differentiate or anti-differentiate a power series, it is not difficult to do, which means we can find a power series representation for a function like this. Wait a second. This inverse tangent function coming out of nowhere. Let's go back a second and see if we recognize what we've done. We have a power series representation for 1 over 1 plus x squared. How does that relate to inverse tangent? Well, they're derivatives or antiderivatives of each other, depending on how you're looking at it. So let's go ahead and say f prime of x, the derivative of inverse tangent, is 1 over 1 plus x squared. And we have a power series representation for that. It was the alternating sum with even exponents. So what we can do is say that f of x is equal to the definite integral from 0 up to x of this power series. Now I'll use t here instead so I don't get too messed up with my variables. Oh, dt. See, I already did it. There we go. Or if you wanted, you could go back to Calc 1 and find the antiderivative family and then solve for your constant of integration. But this is how we've done things at the beginning of this course, right? So what we can do, well, actually, you know what? Maybe I'll do this first. I'll show you where this is coming from. There you go. All right, so now we've got our integral from 0 up to x of the sum from k equals 0 to infinity of negative 1 to the k t to the 2k dt. What you'll notice is that if this is the antiderivative of a sum, isn't that really just the sum of the antiderivatives? We can split up definite integrals based on doing it term by term. So this is really the sum of the integral from 0 to x of negative 1 to the k t to the 2k dt. What I might do is just start thinking about what we're actually going to do here. We're going to add 1 and divide, and then evaluate from 0 to x. And when I say add 1 and divide, what I'm really talking about is doing that to the exponent. I've still got this negative 1 to the k, and now I'm going to evaluate this from 0 to x. Notice that when I plug in x, I'm just going to get the power series from k equals 0 to infinity of negative 1 to the k, x to the 2k plus 1 over 2k plus 1. And when you evaluate this at 0, you're going to have a whole bunch of zeros over 2k plus 1s. And so we really could say minus 0, but I won't really do anything with that, because why would we? Another way that you could have done this is to just use an indefinite integral, find the general antiderivatives, and tack on a plus c. And then use a point on the inverse tangent function, 0, 0 is fine, to solve for your constant, which is going to be 0. What's our interval of convergence? What we'll say is that differentiating and anti-differentiating does not change when things converge or not, other than it could change endpoints. So if you want, you could try and take a look and see, is this going to converge at negative 1 or positive 1? And things might end up being open or closed based on that. What you'll notice, though, is that all of the exponents here are going to be odd, right? And so if you put in negative 1 here, you're going to end up with a negative 1 to raise to an odd exponent multiplied by this alternating thing. And then we'll have some alternating harmonic stuff, and so we could hopefully see what's going to happen with these endpoints. So I'll leave these off for now, and I'll let you take a couple minutes to just think about all that. Pause the video, see if these endpoints are going to be included or not, and then everything should go pretty well from there. All right, so hopefully you've done some alternating series tests on these and found that when you plug in negative 1 or positive 1, you get almost like an alternating harmonic series. It's not actually, our denominator is 2k plus 1 instead of just k, but it's got the same kind of behavior. And you can apply the alternating series test to show that these do converge. They converge conditionally, not absolutely, but that's fine. The series itself will converge when x is equal to 1 and when x is equal to negative 1. So our interval of convergence for this inverse tangent function isn't much different than what we started with, but we do include the endpoints. Hopefully that's helpful to see. Take a look through all this stuff. Make sure that you can understand how these properties are working. But remember, we're really trying to connect everything back to this regular old geometric x to the k thing, and once we can do that, we can string together other series. From here on out, we maybe can say things like, okay, I know what the inverse tangent power series is, and so maybe if I can relate some other function to inverse tangent, I can use that connection to come up with another power series. So we'll play around with that, but we'll also come up with a nice way of doing power series construction in general in our next video.